Time to pull out the calculators. Let's do some stoichiometry calculations in reference to precipitation or double replacement reactions. Now, the first time I read this through, I really just want the balanced equation. I need that for any stoichiometry problem. Eventually, I want to know the mass of solid sodium chloride that must be added to 1.5 liters of a 0.1 molar silver nitrate solution to precipitate all the silver ions in the form of silver chloride. You'll be doing this reaction in the lab, so you might want to put a star by this one. We'll do a similar calculation before we go to the lab. We've got sodium chloride, +1 -1. We're going to add that to a silver nitrate solution. +1 -1. If the silver isn't noted otherwise with a Roman numeral, we can always assume silver is +1. Well, this is going to be nice. Let's do the switch. Switch the positives or the negatives. Silver chloride and sodium nitrate. Now this was all +1 -1s, so the products are neutral and the equation is balanced. I like that. Now, to be honest with you, the last video we were looking at net ionic equations and splitting up all the aqueous reactants and products, and it got a little bit more in depth than just writing a formula equation. Now, sometimes as part of a free response, one of the questions might be, write the balanced net ionic equation. And in that case, I would probably start with a formula equation, and then I'd scale it down by canceling the spectators. Let's say this was your free response question. Nowhere does it ask me for the equation. Now, I have to write the equation because I can't do the stoichiometry if I don't know the ratios and the formulas. But that balanced equation is not really my final answer. Then you can just leave it as a formula equation. This is totally fine. This is all I need to solve the stoichiometry problem. And in fact, you really don't have to put phase symbols in if that's not going to help you with this particular calculation. In this case, it really doesn't. I know that the silver chloride is going to be the precipitate. I want to collect all the silver in the form of silver chloride. So you can leave the equation just as is here. It's not really part of my final answer, although I need to show it so that I can prove to the reader that I acknowledge the ratio in the balanced equation. Stoichiometry is all about ratios. Okay, so let's see what we have. We've got some silver nitrate solution, 0.1 molar silver nitrate. We have 1.5 liters. Now, in a lot of the stoichiometry problems you did in first year chem, they gave you grams, or even in chapter 3, often they started us with grams of reactant. Well, this time it's a solution. Who cares? Because the first step was getting moles. If I wanted to compare different substances in a chemical reaction, I was looking at the mole ratio, a 1-to-1 ratio in this case between silver nitrate and sodium chloride. Oh, well, I can get moles from a solution if I know the molarity and I know the volume. That's not such a big deal. All I got to do is cross multiply and solve this thing for moles. So I'm going to have 0.150. We'll say this 0 is significant. It's after a number that has a decimal. And that's the moles of silver nitrate. So solution stoichiometry is really not a big deal. They just often start you with molarities and volumes, and the first thing we do is get them into moles anyway. Okay, so now I know moles of silver nitrate, and I want to figure out how much sodium chloride I need to completely react all that silver. I want to completely react this silver nitrate compound, so all of the silver is present as silver chloride on the product side. So I want to know how much sodium chloride do I need. Oh, well, this isn't so bad. It's just stoichiometry. We've got 150 moles of the silver nitrate. And if I wanted to be nice and proper, I would cancel moles of what I have. Since it's in moles, we can switch it over to what we want. The sodium chloride. Hey, it's 1-to-1 ratio, so it doesn't do me anything. But it makes me happy to cancel out those units, so I keep it in there. And then finally, they ask for mass. What mass of solid sodium chloride? So let's get this out of moles and into grams. 1 mole. I'll add it up on the periodic table. Yeah, I don't know, pretty close to 58.44. Well, that wasn't so bad at all. This is called solution stoichiometry, where you're getting your moles from a solution. That's not so bad. Plug this in our calculator and we're all set to go. This would come out to be with 3 sig figs. My original has 3. How about 8.77 grams of sodium chloride? Now, what you're going to find in the lab is that we may add a little extra. If I want to make sure that all the silver gets reacted, I need exactly 8.77 grams of sodium chloride. If I add a little bit extra, then I'm kind of like erring on the side of caution. Like by adding extra chlorine ion, I'll know that I have enough to react all the silver. Now, I may have some excess chlorine after the reaction is done, and that's fine, because I'll know that all the silver has reacted with the chlorine. And that's what they're asking for in this one. So realistically in the lab, I think it'll say once you calculate the exact amount, now it might even say double it, or it might say, bump that up to the nearest whole number to make sure that you have enough chlorine to react all the silver. Okay, so that one's not so bad. This next one that I want to do is actually really fun. I like these. There's one in the homework that's really similar to this guy. Da-da-da. I believe it's number maybe 50 something, 51 or something like that. This is a good one. I love this problem. I have 2 liters of a 0.025 molar sodium sulfate solution added to 1.25 liters of a 0.05 molar lead nitrate solution, and I want to know what mass of precipitate is formed. Because I know that one of my products is going to be sodium nitrate, and anything with sodium, anything with nitrate is aqueous. What mass of lead 2 sulfate precipitate is formed? And then I want to calculate the concentration of all other ions remaining in the solution after the reaction takes place. Ooh, this is fun. That's going to be the spectators. What's the concentration of all the other spectator ions that are just swimming around in the solution, but they weren't really part of the chemical reaction? Okay, first step, we need the balanced equation. Sodium with sulfate plus 1 minus 2. I need 2 sodiums. Lead nitrate. Lead nitrate. Lead 2 nitrate. We need 2 nitrates. Okay, let's make the switch. I'll bring lead with sulfate, sodium with nitrate, and check all the charges. Plus 2 minus 2. I like that. Plus 1 minus 1. Sweet. And last thing we should do is balance this thing, huh? I need 2 sodiums and 2 nitrates. Easy. Now again, this is not part of the final answer, but I have to show the balanced equation because I need to prove that I know the formulas and the ratios in order to do any kind of stoichiometry. Now, since they're not specifically asking for the balanced equation, I'm okay leaving it like this. I don't have to scale it down to a complete or a net ionic, but I might actually put the phase symbols in. These originals were aqueous. Aqueous. This lead sulfate is going to be my precipitate, because I know anything with sodium and anything with nitrate is also aqueous. Oh, well, that's not so bad. Let's see what we got here. We have two solutions, and we want to know between the two solutions, do I have a limiting reactant? If so, I'm going to use that limiting reactant to figure out the amount of product formed. So let's turn these solutions into moles. So here's the solution part of the stoichiometry. We've got 0.25 molar sodium sulfate. Molarity equals moles per liter. There's 2 liters. We're going to solve that for moles. And we'll do the same thing with the other solution. It's 0.05 molar lead nitrate. And that's moles per liter. What do we got? 1.25. So we'll cross multiply and we'll throw these guys into moles. That's not so bad. So this is going to be 0.05 moles of sodium sulfate. And then we cross multiply 0.0625 moles of lead nitrate. All right. So now actually this is kind of sweet. Next thing I would do is figure out limiting and excess, because I need to know if there is a limiting. That's the one I'll use to figure out the amount of product formed. Check it out. On the reactant side, it's 1-to-1 ratios between the sodium sulfate and the lead nitrate. If it's a 1-to-1 ratio, then automatically whichever one has smaller moles, that's my limiting reactant. So I don't have to do anything fancy. I just have to use my noggin a little bit. But I can tell you that this is my limiting, and this lead nitrate's my excess. How do you like that? That's not bad. I have to acknowledge the limiting reactant, because I'm going to use this guy then, the limiting reactant, the sodium sulfate. That's the one I'll use to figure out how much product is formed. All right, so let's do that. This isn't bad. That product is a solid, and we would measure the solid in grams. So I'm going to start with my 0.05 moles of sodium sulfate. I do not want to know about the sodium sulfate, so we'll cancel that. Let's get this over to the lead sulfate. We can go moles of lead sulfate. And again, I get it. It's a 1-to-1 ratio, but I like to cross them off when they cancel. And then finally, we'll turn this into grams. So cancel moles of lead sulfate. Let's get it into grams. So I just have to add up the molar mass of lead sulfate. Lead, sulfur, and 4 oxygen. He's a big boy. 303.26 grams per mole. Cool. Let's cancel out moles. Plug it in my calculator, and I am cruising. Well, kind of. What do we got here? With 3 sig figs, the first 0 is not significant, but the 2 at the end are. There's a decimal spot in the number. I'm going to say 15.2 grams. There we are. 15.2 grams of lead sulfate precipitate. That wasn't bad, right? Hopefully. Okay, so now here's the part that's kind of new. Calculate the concentration of all ions remaining in solution after the reaction has taken place. Interesting. So first we have to decide what ions are in the solution after the reaction has taken place, right? That's the tricky part. Okay, the limiting reactant. Let's write this in. This was limiting, this was excess. The limiting reactant is supposed to get completely consumed. So on the product side, I should not have any excess sodium or sulfate. But I have to kind of look at what form it is in on the product side. So for example, that sulfate ion, all the sulfate will turn into lead sulfate precipitate. There will be no extra sulfate remaining in the solution. All the sulfate turns into lead sulfate. It's part of the limiting reactant. But what about the sodium? Yeah, the sodium was part of the limiting reactant, but on the product side, now it's still aqueous. The sodium is a spectator. So even though, yeah, he's part of the limiting reactant, he doesn't change in any way. So all the sodium that was present in this original solution will still be present on the product side as an ion in solution. So the first ion that I'm going to look at is the sodium. So here's what we're going to do. Let's kind of draw a line in the sand here. Let's look at sodium first. Originally, when we calculated moles, we had 0.0500 moles of sodium sulfate. Now, I don't have to worry about the sulfate. So I'll kind of like cross that guy off. He's all part of the precipitate. There will be no sulfate remaining as an ion in the solution. But the sodium is a spectator. He's aqueous on both sides. Okay, so if I had this many moles of sodium sulfate and it's in solution, I actually need to multiply that by 2 to get the amount of sodium ions. So this is really 0.1 moles of sodium plus 1 ions in the solution. All the sodium ions from the original sodium sulfate are still present on the product side. I mean, now on the product side, they're in the form of, on paper, sodium nitrate. But since I have that labeled as aqueous, it really means that the ions are just separated. All of the original sodium ions are still present on the product side. Interesting. Okay, so I don't have to worry about sulfate. Now let's look at the lead nitrate. Lead nitrate. Let's look at nitrate first, because something similar is going to happen. Nitrate. All of the nitrate ions in the original solution are still present as ions on the product side. They're all aqueous. It's another spectator. So I can do the same thing with the lead nitrate. The amount that I originally had was 0.0625 moles of lead nitrate. In solution, there's 2 nitrate ions per mole, so we'll multiply that by 2. And here we go. We'd have 0.125 moles of nitrate ions. These are the 2 easiest. They're aqueous on both sides. They're the spectators. So when they say calculate the concentration of all ions remaining in the solution, here's 2 that are definitely present in the final solution. Okay, so now we've got the moles, and molarity is moles per liter. Now, sometimes they'll write this in the original problem. They'll say, assume volumes are additive. And that just means that once I combine these solutions together, I had 2 liters and I had 1.25 liters. The final volume is 3.25 liters. If they don't say that, it's always safe to assume that the volumes are additive. And that's really what it means. Add the volumes to get the total final volume. So now all I got to do is a quick little calculation. And we need a little more room. Well, not that much room. Okay, this will work. And we're going to switch these into concentrations. So the sodium ion is 0.1 moles. And once I join the solutions, the final volume is 3.25 liters. Oh, well, that's not too bad, right? I think I can handle that. 0.1 divided by 3.25 gives me about 0.0308. Let's go 3 sig figs. Okay, so there's the sodium plus 1. That's one of the ions remaining in the solution. Now I got to find the other one, the nitrate. We can do the exact same thing. The nitrate. It's 0.125 moles in 3.25 liters of total volume. So plug this in our calculator and we'll leave 3 sig figs. So let's say 0.0385. And that's the nitrate. Minus 1. I like that. Okay, so these are usually the 2 most obvious ions remaining in the solution. The spectators. If I look back at my original balanced equation, the sodium is aqueous, the sodium is aqueous. The nitrate is aqueous, the nitrate is aqueous. So all the sodium and nitrate are ions in the solution after the reaction has taken place. There's one more ion that's secretly hiding in this solution. Have you found him? It's not the sulfate. Sulfate was part of the limiting reactant. All the sulfate ends up as lead sulfate precipitate. I bet you see it now. It's the lead. Lead was part of the excess reactant. Now, we took care of the nitrate. All of the nitrate in the original solution was present on the product side. But there's going to be some extra lead. Most of the lead turns into lead sulfate precipitate. But there will be some excess. So we need to figure out how much excess lead is in the solution, and then we'll do kind of the same thing. We'll divide it by our total volume. So we can look at this really simply. It was a 1-to-1 ratio. So when these guys react together, if I had 0.05 moles of sodium sulfate, I'll react 0.05 moles of lead nitrate, and I have excess. So to find the amount of excess lead nitrate, all we have to do is subtract these two. And they're in moles, and that's good. That's kind of the unit that I want them in anyways. So let's do that. Here's the other guy. I had 0.0625 moles of that lead nitrate, but I'm only going to react 0.05 moles of it. So this is what gets reacted. A little stinker lead. This is what I have. The difference is the amount excess. This is usually the ion that people will forget about because they don't tell me, hey, calculate the concentration of the following ions in the solution. It just says, whatever's left over, you figure it out. Great. 0.0125. Now that's going to be moles of lead nitrate. excess. For every 1 mole of lead nitrate, there's 1 lead. So I can calculate the molarity of the lead ions. Lead plus 2. There's going to be 0.0125 moles of excess lead ions. And the total volume is still 3.25 liters. All right, so plug this in. Divided by 3.25. With 3 sig figs, we'll say 0.00385. Ah, close, but it's 0.00385. And that's the molarity of the excess lead ion. There they all are. The two obvious are the spectators. The tricky ion is the one from the excess reactant. Some of it, actually most of it, gets reacted and turned into a precipitate. But there will still be some excess lead in the solution. I love this question. This is great. It's got so much solution in it. There's the stoichiometry, the concept of spectators and soluble products versus insoluble products. It's got the limiting and the excess. This is a beautiful question. You could expect to see something like this on a free response question in a AP test.